Welcome back. I'm going to work through Unit 7 in class worksheet, and question 1 asks you to draw 3 polar and nonpolar amino acids and explain why they are polar and nonpolar. Instead of me drawing them out, I'm just going to use the reference sheet, although I encourage you to draw them out. And I'm going to explain why the polar ones are polar and why the nonpolar are nonpolar. Okay, so these 3 are polar. This is serine, arginine, and asparagine. And they are polar because they each contain at least one polar bond. You can see here that or at least the side chain rather, contains at least one polar bond. As we've talked about in class, all amino acids have the backbone that has several polar bonds. All amino acids have that, whether they're polar or nonpolar. However, the ones that are considered polar in the groupings have polar bonds in the side chain, which is down here. Another term we use is the R group. So you can see here in the R group of serine, there's a C, then 2 H's, and an OH. And the OH bond is polar, and the CO bond is polar. So that's why serine is polar. Arginine has several polar bonds in its R group. There are lots of nonpolar bonds. You can see CC bonds and CH bonds. These are all nonpolar. However, the CN bond, the NH bond are both polar, and there are several examples of those in the arginine R group. For asparagine, we see there's the CN bond, the NH bond, and the CO bond. All 3 of those are polar. So each one has at least 2 examples of polar bonds, and that is what makes the amino acid behave like a polar group. Okay, for the nonpolar, I'm going to start over here with tryptophan. Tryptophan, as we can see from the skeletal structure, has 3 polar bonds. It has a CN bond here, a CN bond here, and an NH bond. However, the rest of the bonds are all nonpolar, and tryptophan behaves like a nonpolar amino acid. So looking at the proportion of nonpolar bonds versus polar bonds, we see that tryptophan is in fact more nonpolar than it is polar. So that's why it's classified in the nonpolar group. Over here with leucine and isoleucine, both of these are, at least in their side chains, are entirely nonpolar. There's no polar bonds in any of these side chains. So that's why they are in the nonpolar grouping. Okay, let's move on to question 2. Question 2 asks you to draw the tripeptide, aspartic acid, cysteine, phenylalanine. So just like with every peptide that we draw, we begin the same way. Start with NCC for each amino acid. Since there's 3, I need 3 NCCs. And I didn't specify pH here, so I'm going to go ahead and do that now. Let's say this is at pH 7. So I'll start at the N-terminus. The N-terminus is the aspartic acid. There's NH3+, and then there's that alpha carbon here, and there's an H coming off of that, and then we have the R group, which for aspartic acid is this grouping. This has got a negative charge on it instead of an H because we're at pH 7. If we were at pH 2, there would be an H on there. And we have the peptide bond here. This is the peptide bond. And then we have the next amino acid, cysteine. The R group for cysteine is CH2SH. It's fine to draw it just like this, or you could put the SH up here. Doesn't really matter. And then the second peptide bond. Then we have phenylalanine. Phenylalanine has an aromatic group on it. So that's the R group for it. And then finally the C-terminus, which is going to match our acid over here. If there's a negative charge here, there should also be one here, for at least the problems that I'm giving you in class. Alright, so that's the tripeptide aspartic acid, cysteine, phenylalanine. Next one is a tetrapeptide. I probably didn't leave myself enough room here, so I'm going to write a little smaller. I'm going to begin with the same way, NCC, NCC, NCC. And I'm going to start with the glutamic acid. So the next carbon is going to be the R group. There are 2 carbons, 2 CH2s, and then the carboxylate ion here for glutamic acid. Then the first peptide bond, and then glutamine. Glutamine contains an amide bond. Amide bond here. And then the second peptide bond, and on to histidine. Histidine kind of has a funny structure. That's a 5-membered ring with a nitrogen, with actually 2 nitrogens rather. And since we're at pH 7, I'm going to draw this without the positive charge, although if you drew it with the positive charge, that would be fine. You could draw it with an H. That's the way it shows on your reference sheet, with an H. So I'm not going to be super picky on that. And then the third peptide bond, and then finally leucine. And then the C terminus. Since we're at pH 7, again, this is going to be negatively charged, just like this one is over here. All right. Now for the fourth one, draw the tripeptide lysine, glutamic acid, and glycine of pH 2. NCC, NCC. Hope to drill that in your head. I'm going to start with the C terminus and notice that now I have an H because I'm at pH 2. And then the N terminus is going to be positively charged. We begin with lysine. You can do this one of 2 ways. The shorthand would be just to write it like so. Whoops. Pull up the page there. There are 4 CH4s in a line. On your reference sheet, you'll actually see the 4 CH4s, so excuse me, 4 CH2s written out. But you can write it in shorthand. And then the amine at the end, positively charged. Just like this one's positively charged, this one should be. And I realize this is kind of like a hybrid condensed line bond, and that's fine for drawing these. You can write it entirely condensed or as a hybrid like I've done. First peptide bond linkage, and now we're on to the second amino acid, glutamic acid. 2 CH2s and a a carboxylate ion. Because we're at pH 2, I need to fill in that H. Then the second peptide bond, and finally glycine. Glycine being the having the R group of just H. Now with this one, I'm going to go ahead and label everything. I'm going to box in all the R groups here. I'm going to point to the C terminus and the N terminus. I'm going to circle the peptide bonds. Okay, so everything's kind of labeled there. R groups in the boxes, circle around the peptide bonds, and then the C terminus and the N terminus. All right, on to page 2. Page 2 asks me to draw the tripeptide glutamine, aspartic acid, arginine at pH 7, then draw the hydrolysis product of this peptide at pH 2. Okay, so this would be like the form it would exist in before you ate it, and then you eat it and it gets to the stomach, and is hydrolyzed at a pH of 2. So let's do that. Over here, I'm going to start way to the left. NCC, NCC times 3, and begin with the N-terminus. Glutamine has the amide bond down here, then the first peptide bond, then aspartic acid. Since we are at pH 7, I need to make that a negative O here, double bond here, negative O there, and then the second peptide bond, and then finally arginine. Arginine is going to be 3 CH2s, so you can do it like this, and then kind of has an interesting structure. This is going to be positively charged because this nitrogen has 4 bonds to it, 2 to hydrogen, 2 to carbon, so it's positively charged, and then 1 more amine. So there's actually 3 amines in the arginine structure. And then, of course, the C-terminus. Notice how these two are the same. And then we're going to draw the product from the complete hydrolysis. And so let me just show you what water is going to do. Water will break the bonds at 2 places. It will break a bond here, and then water will break a bond here. So essentially we need 2 waters. But it breaks right in between that peptide bond linkage. And then we end up with, if you were to just erase this line, erase that line, you would see the 3 amino acids that you're left with. So I'll draw the first one over here, glutamine. And I'm just going to draw this in shorthand. NH3 here, same thing that's there. Save a little space here. And then the C-terminus, this is what's important because we're at pH 2 now. So I've got to put that H there. So this is the glutamine. And I should probably write that water is responsible for the hydrolysis here. You don't have to put 2 waters, you can just put water. And then the middle amino acid, aspartic acid, again NH3+. Since this is an acidic amino acid, I also need to have the H here for pH of 2. And the same thing on the C-terminus here. And then the third hydrolysis product, which is arginine. Kind of a long R group, that one is. And then finally the C-terminus of this amino acid with the H. Okay, so 3 hydrolysis products. Started off with 1 connected molecule. Water broke in 2 places because it breaks at the peptide bonds. And then we end up with 3 complete amino acids as products. For number 8, you can just see the key. I'm not going to actually write all these out, but the key lists them out. It's also in the PowerPoint notes. For number 6 and 7, I will draw these out. It says draw out the amino acids tyrosine and serine and include the interaction that would exist between the side chains. List all the levels of structure where this interaction could occur. Okay, so I'm going to draw these out where the side chains are pointing left and right. So I'm going to start by drawing the side chain for tyrosine here. And then I'll have the side chain for I'll have the side chain for serine here. And then I have the alpha carbon right here. It doesn't really matter how you order this. I'll put the C terminus here and the N terminus up here. And I'm drawing these at pH 7. It's not really that important for this one, which pH it is. It'll be more important for the next one. Okay. And so what we can see here is that we have OHs. And OHs, if you recall, can hydrogen bond. So one of the interactions that can take place, and the primary interaction that can take place, I'll do this in red, is the hydrogen bond between the oxygen and the hydrogen. Okay, so we can actually have two hydrogen bonds here. And remember, we can get this because the oxygen's partially negative, the hydrogen's partially positive. So positive and negative are going to attract. And this is the hydrogen bond. So there's an attractive force that exists between these two amino acid side chains. Now, this says list all the levels of structure where this interaction could occur. Well, it's not going to occur in primary, because this is just the sequence of amino acids. It will not occur in secondary, because secondary is only involving the backbone. Okay? Remember, the secondary will only involve the backbone, and the backbone is this part. And this part does not include the side chains. However, with tertiary and quaternary, yes, both of these can occur. Because remember, with tertiary and quaternary, the side chains are involved in the attraction between amino acids. So the amino acids, or the protein rather, can fold back on itself, and the side chains can come close to each other and attract each other and kind of pull the protein inward and make a fold or a turn in some cases, and make the structure more complete. So for tertiary and quaternary, this interaction could occur, but not primary or secondary. Okay, draw the amino acids lysine and glutamic acid and include the interaction that will exist. I'm going to do this at pH 7. So lysine, the R group looks like this. And I'm just going to draw the positive charge. This is a full ionic charge here. This is a full ionic charge. And then with glutamic acid, I'm going to kind of draw this backwards. Again, full ionic charge. And I'll kind of draw this to express what this Cu means. Right, COO is the same thing as this. And we have a full 1 minus charge. Here we have a full 1 plus charge. And then we have the rest of the amino acid up here, just like we had for the last one. Same thing's true up here. Okay. So hopefully you can see that positive and negative being really close to each other, and especially having a full positive and a full negative, as opposed to this one, which was partial positive and partial negative, these are going to attract each other. And they're actually quite strong. We call this a salt bridge or ionic bond. Okay. Full positive, full negative, they will attract each other. Okay. If the pH were to change to pH 2, this would gain an H and become neutral. Then they would no longer attract each other. So we can see here how pH changes are important for maintaining the structure of a protein. Because if this particular interaction was critical to the structure of a protein and then the pH changed, then that would influence this interaction, and then the protein might unfold. Okay, so if we go back up to the little diagram I drew over here, the same thing's true for number 7. It cannot be primary or secondary because those involve the sequence and the backbone. But for tertiary and quaternary, those involve the side chains, and that is what we're dealing with here. These two are the side chains of the R groups. So that will permit this interaction to occur at the tertiary or quaternary level, but not primary or secondary. Number 8 says, briefly and broadly explain how the enzymes do their work. Well, enzymes bind substrates. Kind of draw a little Pac-Man here. This is the enzyme. This is the substrate. Enzyme and substrate. Okay. And when these two get close enough together, if there's enough of them around that they'll bump into each other in the right fashion, they will form an enzyme substrate complex. Where the enzyme and the substrate are bound together. Guess I should color this in too. And then this allows the enzyme to do its work. So this would be an enzyme substrate complex. And basically what the enzyme does is it lowers the activation energy necessary for the chemical reaction to take place. So let's say this substrate is a protein. And we all know that proteins can be hydrolyzed with water. Well, they're not spontaneously hydrolyzed with water very easily. So enzymes help them become hydrolyzed, help them to essentially break up into amino acids so then our body can use the amino acids to build our own proteins. So the enzyme will bind the protein and then it will orient it in such a way that water can come in and break those bonds, those peptide bonds. So it lowers the energy barrier necessary for the reaction to take place. I know that's kind of a very broad explanation, but that's basically what I'm looking for with your responses as well. Keeping in mind that the enzyme will bind the substrate, they'll form an enzyme substrate complex, and then the activation energy for the reaction that's taking place is lowered, allowing for the reaction to actually proceed at a normal temperature that would be in our bodies. A lot of these reactions wouldn't necessarily take place at the temperatures of our bodies, but because of enzymes, they are able to do that. All right, I hope that was helpful.